11. This is part 1. I also just want to make a quick note. This is where we're going to start switching topics. So up until now, we've been doing what we consider general chemistry. Today will be our first kind of dipping our toes into what is considered organic chemistry. So when you took this class, you're taking the GOB, which stands for General, Organic, and Biochemistry. So we're done with our G portion of our course, and we're moving on to the O portion of it now. Please keep in mind there are certain parts of general chemistry that will still be really useful for us. So if you're still struggling with your Lewis structures, you're gonna have to be really good at those, because organic chemistry, we are going to use Lewis structures all day long. So it is important that you continue to practice with those. We will be doing significantly less math. So if you were frustrated with the gases and a little bit of the thermochemistry we did and like mole conversions and things like that, we're pretty much going to put that stuff on the back burner for a little bit. We'll come back and we'll see a little bit more of it when we get to our biochemistry, but we're going to be doing new challenges now. So unlike before, where it was kind of a plug and chug, if you were good and understood the equation and could figure out what were the variables, you were able to plug and chug it out. Organic chemistry is a little different. It's much more like a problem solving thing. So you're given a situation and you got to go, okay, well, I know what this looks like and I've seen stuff like this before, so I think it would do this. So again, if that sounds familiar to what we did with Lewis structures, it's very similar to that, and we're just going to keep building on that. So some of you who did really well with the general portion may struggle with this, and some of you who struggled with the general portion may excel at this. So this may be, kind of an opportunity for turning a new leaf in terms of different material that we're going to cover. So these are, we're going to be pretty much covering all of chapter 11. Oops, it looks like these should all have 11s in front of them and not 1s. Sorry about that. Just noticed that. Slides are already posted. It's okay. 11.1, 0.2, 11.3, so on and so forth. Sorry about that, guys. These are the subject topics. If you look in your textbook, you do need to read your textbook, guys. I'm putting up in the assignments those suggested kind of chunks of reading to do and when to have them done by, to kind of help make sure that you don't get behind. If you haven't been reading your textbook, the tests and quizzes are going to start getting really, really hard for you. So I really encourage you to read the textbook, come to office hours, email me with questions so that you can stay on top of it. These are some of the general learning objectives that we'll be doing, so I'd encourage you to look through them and kind of understand where we're going with things. So, welcome to organic chemistry. Organic compounds are kind of this huge topic, and obviously most of us have heard the word organic before. Probably you're thinking of something you buy at Whole Foods, right? We know that there are a lot of foods that are labeled organic, but just like we've learned with other things, like the difference between a theory and a law, or precision and accuracy, we have these terms that in our general day-to-day lives have different meanings than they do when we actually apply them to chemistry. And organic is one of those words. Organic has nothing to do with something being healthy or being natural or anything like that. We'll talk about a little bit of how we came up, how the food industry kind of came up with using this term organic. But for our purposes in this class, when we talk about something that is organic, it is a compound that contains the element carbon. Okay? That defines something as organic. So next time you go to like Whole Foods or the grocery store and you see organic table salt, NaCl, you can scream at your lungs, this is false, right? NaCl has no carbon in it, therefore it cannot be organic, okay? By the definitions of what we consider organic in chemistry. Organic is something that contains the element carbon. Now, the first example of someone who was able to synthesize an organic compound from what we consider an inorganic source was Frederick Wohler, and this was back in the early 1800s. So, for example, he was able to do this with urea. If you're not familiar with urea, the natural source of urea is your pee. It comes from mammals, amphibians, birds, urine of pretty much most animals contains urea. And it's a useful compound when doing synthesis and things like that. But it was made from this compound here, ammonium cyanate and heat. And so this ammonium cyanate was not from a person or an animal or anything like that. This was a compound that was able to be produced inorganically, not from like a living creature. And through degradation of heat was able to produce urea, which we know at the time came only from animals. So this discredited this concept of the vital force theory. And the concept of the vital force theory was that all organic compounds are produced through a special force active only in living organisms. So like this kind of, special, there was something special about living organisms, and only living organisms could produce organic compounds that were found in them. And so this was the first time that we kind of found out that this special force doesn't exist. This is very, very important to realize in terms of how a lot of medicines and foods and pretty much anything we have in our day-to-day lives is made. So, for example, many of you may know that aspirin was first derived from willow bark, from the bark of willow trees. People realized that when they chewed on the bark of a willow tree, it helped subside pain and things like that. Basically what aspirin does, right? Lowers fevers, so on and so forth. The aspirin that you get in the bottle today is slightly modified because what came out of the willow bark was salicylic acid, which tended to give people upset stomachs, and so it has been modified so that it's now acetylsalicylate, which will be a little more gentle on your stomach. But the base of it comes from willow bark. When you go to Target, or now I guess everybody's Instacarting everything, and you get a bottle of aspirin, that was not something that was chopped down from a tree and taken from there. That aspirin, that salicylic acid, was produced in a lab. Now, the salicylic acid that comes out of the tree and the salicylic acid that comes out of the lab are the exact same thing. There's nothing special about the one that comes out of the tree. This is something in society that we're starting to see a lot more of that. Oh, it's natural sourced. If the compound has the same formula and the same purity, there's nothing special about it. It's no different than the exact same compound that is made in a lab. And this is something some people struggle with, but on a chemical level, there's nothing special. There's no magical force. There's no vital force that comes from something that comes out of the ground if it's the exact same chemical formula as something that's made in a lab. So this was Wohler's discovery and kind of contribution to the scientific community. So, as we said, organic chemistry is going to be the study of carbon-containing compounds. We have a few exceptions that we don't treat like organic chemistry, and we've seen a couple of them already. Carbon monoxide, carbon dioxide, the carbonates, which are part of our polyatomic ions, and cyanides. And this is partially because these carbon-containing compounds, if you see, they all have N's and O's with them. Oftentimes the O and the N are really electronegative. They kind of behave a little more ionically, things like that. They don't really behave like organic compounds behave. And so these are our exceptions. So I know it's frustrating for people to have exceptions, but we do have a few of them. Everything else that contains a carbon, though, we're going to say is organic chemistry. Inorganic chemistry is a study of everything else. And the elements. So pure carbon by itself is part of inorganic chemistry. We're just talking about like a diamond, which is just all carbon, or graphite, which again is all carbon. If it's just got carbon and nothing else in it, then it would technically be an inorganic compound. If it has carbon but isn't one of these and it's bound to other things, then it would be an organic compound. Typically, organic compounds will be covalently bound. Inorganic compounds are ionically bound. So that's kind of a little hint when you're looking at a compound. So we have just some general properties of the differences between organic compounds and inorganic compounds. And you may look at this and go, yeah, some of these seem very obvious. So something like wood or paper is an organic compound. Something like table salt or steel is an inorganic compound. So if we take those two examples, we can go through and look at each of these. The bonding within the molecule. Well, an organic compound is going to be covalent, where ionic compounds are pretty much always going to be ionic. The forces between the molecules. Think about this. This is an inter-ER molecular force we're talking about. If it's covalent, that means we're going to have London dispersion, because we know everything has London dispersion. It might be polar, so it might have some dipole interactions, and it might have an OH bond or something like that, so it might have some hydrogen bonding. But remember that in comparison to something like an ionic compound, where the polarness of the bond is extreme, right? It's not slightly polar, slightly positive, slightly negative, like we have in a dipole. It's an actual positive and negative. So the intermolecular forces between inorganic compounds, ionic compounds, is much, much stronger than the ones in organic compounds or covalent compounds. So think about that in terms of things like boiling point and melting point, and things we've talked about before, right, in Unit 1 and 2. We know that the stronger the intermolecular forces, intermolecular forces, the more energy it would take to break apart that molecule. The more energy it takes to break it apart would mean a higher temperature to boil it or a higher temperature to melt it and things like that. Normal physical state. Again, because of those weaker, relative to inorganic compounds, weaker intermolecular forces, typically we see them as gases, liquids. If they're solids, compared to an inorganic compound, they have relatively low melting points. Inorganic compounds have high melting points and are pretty much always solids. So again, think of the melting point of table salt. How hot would it have to be for the table salt to actually melt? It's not going to happen on your stovetop. Think about all the other things that you have that you could melt. So it's significant when you start comparing these two. Flammability. Most organic compounds are flammable. We can catch them on fire. Inorganic compounds, not so much. When was the last time you saw a piece of steel on fire? Now, if you weld and stuff like that, hopefully you also realize how hot that had to be for it to catch on fire. Solubility in water. Organic compounds are going to be often not very soluble. And this is because organic compounds are mostly made up of C and H bonds. So think about that for a second. If organic compounds are pretty much going to have a bunch of CH bonds in them, does that mean that the compounds are mostly going to be polar or nonpolar? Hopefully you said nonpolar. That's right. And we know water is polar, so like dissolves like. These don't mesh up too well. Inorganic compounds, on the other hand, are typically ionic. And we know ionic compounds are very, very polar, and so much so that when we see NaCl and the state of matter is aqueous, we know that's the secret language of I know that you know that I know. It's really Na plus and Cl minus. These are very soluble in water. Conductivity in water. Now we're talking about electrolyte solutions, right? So if it's not very soluble in water, not going to be a very good conductor of electricity because we're not going to have a whole lot of ions present in the water. Whereas we know that most ionic compounds are very soluble in water, which means there are going to be a lot of ions present, which means it would be a good conductor of electricity because there would be a lot of ions present. The last one, this is kind of new for us. Organic compounds, typically the reaction is slow in comparison to things like inorganic compounds. So when you think about this, think about making a cake, right? There's a lot of organic chemistry that goes in baking and cooking. And those things take time, they take heat. The reactions are much, much slower in comparison to something that's inorganic. So real quick, I'll give you a moment to give this one a try, so pause it and answer the following question. Hopefully you got urea. Remember, carbon dioxide is one of our exceptions to the organic carbon-containing compounds. Go ahead, pause the video, and answer this question. Again, this question, is which one of these is not true? Organic compounds tend to react very slowly, so this is the correct answer down here. One last thing, we will be going through using all different representations of how we draw our Lewis structures. So our planar representation, this is the one that we're most familiar with. We already did the lab in class where you got the opportunity to play with the model kits. So you already got to see the 3D structures. The space filling model is essentially what we use model kits for, right? And then the tetrahedral arrangement like this. Okay, we're going to briefly in this class talk about the concept of hybridization. I will be posting in the extra help section for this unit a whole lot of videos that have much prettier pictures than anything I can draw to help describe this, but we do need to go through some basic concepts of this. So let's think about this for a second. We know that organic compounds, which is now our focus, are predominantly covalently bound. And we know covalent compounds, they form their bonds by sharing their valence shell electrons, right? Covalent, sharing of valence shell electrons. So for example, let's talk about carbon, right? Because carbon is we're going to do a lot of carbon because it's organic chemistry. And so here is the electronic configuration, right? The electronic diagram of carbon. We know carbon has 4 valence shell electrons, right? We know it has a full 1s, so 1, 2, 3, 4, 5, 6. Look on your periodic table. Number of protons and electrons in a neutral carbon atom, 6, right? So we know that the valence shell electrons are the ones that are in the outermost layer. So in that case, this would be the n equals 2 layer. So we have a total of 1, 2, 3, 4 valence shell electrons. Does everybody agree with that? So we need 4 more valence shell electrons to make our octet. We know this, and we're hopefully very comfortable now with the idea that carbon makes 4 bonds, whether it's 4 single bonds, 2 double bonds, a single bond, and a triple bond. However, there's a lot of different ways it can make those 4 bonds, but it needs to make 4 bonds. Now, let's think about this for a second. If I had something like CH4, we know that CH4 is symmetrical, right? I could have it right side up, I could turn it upside down, I could turn it to the left, I could turn it to the right. And no matter how I look at it, all the CH bonds are equal to each other. But how does that happen? How do we share 4 electrons with hydrogens when this is what our structure of the carbon looks like? 2 of our valence shell electrons are already paired off, and 2 of them are here, and this doesn't have any of them. So how does it work that each hydrogen makes a single bond with the carbon? Plus, we also need to remember, right, that the 2s is lower in energy than the 2p. So if that were the case, that somehow those 4 hydrogens made bonds with individual electrons when they were like this, some of those bonds would be higher in energy than others, which is also not true. So what we see happen is this concept called hybridization. Just like the hybridization when we say we have a hybrid vehicle, which means it takes both gas and electric, we're going to hybridize and combine our 2s with our 2p. And when we do that, we get what we call an sp3. We get 4 sp3 hybridized orbitals. And I'll go through this. I have 1 s orbital, and I have 1, 2, 3 p orbitals, for a total of 1, 2, 3, 4 orbitals, right? These 4 orbitals are involved in the covalent bonding. We know carbon in CH4 is tetrahedral, right? It has 4 electronic groups around it, which means we're going to need 4 different orbitals or 4 different spots that bonds can occur. So it's going to use all 4 of these, and they're going to kind of mesh together. And we end up with 1, 2, 3, 4, what we call sp3 orbitals. S, 1p, 2p, 3p. That's why we call it sp3, literally sp3. That's why it has that name. And we can count it out. 1, 2, 3, 4. That's how we end up with 4. The important thing here to also note is the energy. The sp3 is slightly higher in energy than the S2 and is slightly lower in energy than the 2p. So it's a hybrid, right? It's not as high in energy as the 2p, but it's not as low in energy as the 2s. But now they're all the same energy. And now each of these spaces can go make a bond and share an electron with one of the hydrogens in the CH4. That's what we're talking about when we talk about hybridization. So if we have an sp3 orbital, we know that the s orbital is kind of like a ball, is spherical shaped, and the p orbital kind of looks like this. It looks like a dumbbell. So when we combine the s and p together, it looks like a lopsided dumbbell. So when we have them all together, it looks something like this. So this is a representation of CH4, where the green stuff is the carbon with its 1, 2, 3, 4 sp3 hybridized orbitals, and these white balls represent the hydrogen that it's going to go make bonds with, right? And hopefully you can see the tetrahedral structure that we know CH4 has. Whenever we have a single bond, that will be the sharing of two electrons that overlap, and this would be what we call a sigma bond, represented by this symbol here or the word sigma. When we have a double bond or a triple bond, we'll have one sigma bond, because we're always going to have at least one sigma bond, and then any additional bonds on top of that. So in a double bond, we would have a sigma bond and then a pi bond. In a triple bond, we would have a sigma bond and two pi bonds. So we'll look at that as well. So when we have 4 sp3 hybridized orbitals, it can make 4 bonds. So anything that is going to be tetrahedral in its electronic configuration will be sp3 hybridized. Okay? So you will have to know your geometry still to be successful with hybridization. Your homework will have a lot of really nice practice with this, but that's something where if you were not very good with your geometries, which goes with your Lewis structures, you're going to have to go back and look at these. I do have some really good resources that I've posted to use that online virtual modeling kit and things like that as well. Okay, so carbon we know can bond to other carbons, right? There's no limit to the number of carbons that could become covalently bonded to each other. So what I mean by that is I could have a chain that would go C, 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 C for 500 carbons in a row. And then yes, you know, if it's just a hydrocarbon, the hydrogens would fill in the other 4 bonds that it would need to make. But this is part of the reason why we have so many organic compounds, is because carbon can make 4 bonds. So there's a lot of different things, a lot of different combinations we can make with this. So organic compounds can range from very simple things like methane, which is CH4. This is ethane right here, to very, very complicated molecules ranging with over 1 million carbon atoms in them. And we'll actually look at some of these when we get to our biochemistry. So basically proteins, enzymes in our body, these are all multiple millions of atoms, millions of carbon atoms. Some of them are enormous. When we start thinking about things like hemoglobin, we'll start seeing how big these molecules can get. But don't get overwhelmed. We're not quite ready to go do that yet. The next concept we need to talk about for organic chemistry is something you may have already run into when doing your Lewis structures, and that's the concept of isomerism. So you may have heard of an isomer before, or maybe if you do exercises, you've heard of an isometric hold or an isometric exercise or something like that. Basically, an isomer or an isometric triangle. We know that an isometric triangle is a triangle, right, if you take in geometry, where all the sides are the equal, right? An isometric hold or an isometric exercise when you're doing a workout is something where you're really not moving, right? So you're not having any differences going on, and you're just kind of holding in, right? There's strength involved with that. So isomerism in chemistry, what we're talking about is a property in which 2 or more compounds, right, we could have multiple compounds, have the same molecular formula, but the arrangement of the atoms is different. So we're going to have a couple different types of definitions of isomers that we're going to see, but the first one we're going to talk about is a structural isomer. And this is an isomerism in which the atoms are bonded differently. So let's kind of play with this word structural. Let's say I have a Lincoln Logs kit, like a kit to build a little house. It's got 4 walls, a door, and 2 windows. Now, person A might build the 4 walls and put the door and 2 windows on the same side of the house. Person B puts the door on the front and the 2 windows on each side. And person C puts the door on the front and puts the windows on the back side. All the same parts, but different houses, different structures. So that's what's happening in a structural isomer. If I have the formula C2H6O, I can arrange or put together that molecule in different ways where I have different bonds occurring. So we have 2 different structural isomers for the compound C2H6O. We have ethyl alcohol, also known as ethanol. If you're 21, this is the fun stuff you can drink. And dimethyl ether. Okay, now we can see we have the 2 carbons bound together and we have a hydroxyl OH group up here. In this case, the other way we could do it is have 2 groups where we have CH3, CH3, and sandwich the oxygen in between. We'll find out later this is a group called an ether, and when we have an OH group like this is called an alcohol. So we're actually going to learn how we define these different groups. And these have very different properties to them. If you drink this, you'll probably die. If you drink this in moderation, you can have a good time. Very, very low boiling point, relatively higher boiling point when compared between the 2 of them. So they do very different things based on the fact that they're structurally different, but they have the same formula. So they are considered structural isomers. So I'll give you the opportunity now to try and draw these out on your own. Again, I encourage you to pause and actually go through these and try doing these. Make sure that your bonds all make sense and that we can see the different relationships to them. You don't need to worry about naming them just quite yet. We will be learning how to name them though. All right, so I'll pause here. Go ahead and figure out the best answer for this question. Covalent bonds that carbon can make are 4, right? We know that it can make 4. In this case, this is 4 single bonds. We know it could do 2 double bonds, a single bond, and a triple bond, 2 single bonds, and a double bond. A lot of different ways it could do it, but always needs to make 4 bonds. And don't worry about this word alkanes. We're going to be talking about that in a minute. So now we're going to start talking about this concept of a functional group. So remember how I called out earlier an ether and an alcohol? We're going to start learning, because there's so many different organic compounds, just because of the different ways that carbon can make all sorts of different bonds, there's millions and millions and millions and millions and millions and millions of compounds, and new compounds are being discovered every day. So it's really hard to keep track of all of them. But we notice when they have certain groups of atoms bound together, they start behaving similarly. So we started kind of putting them in categories. So it's like different flavors. We could have alcohols, we're going to learn about aldehydes, we're going to learn about ethers. For this chapter and chapter 12, we're going to focus solely on hydrocarbons, which, as the word kind of should give you the hint, are carbon-hydrogen containing compounds. And so the first one we're going to talk about are alkanes. A-N-E-S. That's what you're going to have to remember. Alkanes, A-N-E. Alkanes will be single bonded hydrogen-carbon compounds. So we've seen a lot of those. We're also going to learn about alkenes, E-N-E, and those have double bonds, and alkynes, Y-N-E, those have triple bonds, all just dealing with hydrogen and carbon. So we'll go through each of those. Now, we will learn about other functional groups that have nitrogens in them and sulfurs in them and all sorts of other things too. So we will build up a rapport of these different functional groups. To give you an idea, here are some of the ones that we're going to learn. Alkanes, like I said, A-N-E, are going to be hydrocarbons, so things that only contain hydrogen and carbon and only have single bonds. Alkenes, E, will be hydrocarbons that have at least a single double bond in them. They can have multiple double bonds, but they have to have at least one double bond in them. Alkynes, YNE, will have at least a triple bond in them. We'll also learn about compounds that we call aromatic, which are kind of these special double bonded systems. Basically, it's an alternating pattern of double bonds, and we'll learn about why that's special. Alcohols are a functional group that contain that OH, that hydroxyl group that we've been dealing with before. And then ethers are going to be functional groups where we have a sandwiched oxygen. We also will have amines, aldehydes, ketones, carboxylic acid, esters, and amides. Don't freak out. We're going to dedicate a chapter to each of these, so that's why I'm just kind of throwing them out there right now. So let's start talking about how we represent and draw Lewis organic compounds. You're familiar with what we're going to start calling the expanded structural formula. This is a Lewis structure. This is what we've been doing. Hopefully it's, old news to you at this point, but what it shows is every single bond present in the molecule. It shows all the covalent bonds. This is what we call an expanded structure. A condensed structural formula shows a general arrangement but doesn't show every bond. So here, this compound can be represented in two different ways in the condensed formula. CH3 represents this guy right here, CH3. CH2 represents this guy right here. CH2, this guy right here. CH3, this guy right here. We could also write it like this, where the CH2 has been condensed, just like we would if we were writing another formula, right? Where if we put CH2 in parentheses with a 2, we would know this really means CH3, CH2, CH2, CH3. So pause the video here and take a moment to go through and identify and write this in its condensed formula. We know that we're going to typically have these kind of terminal groups on a compound, like we see here. This is a terminal group, it's at the end. We're going to see these a lot. This gets condensed to CH3. We'll learn later that this is called a methyl group, but this is very, very common, so you'll see a lot of it. And an internal carbon will often be a CH2. So CH3, CH2, CH2, CH3. Which again, we can go even lower to condense it more. All right, so I want you to take a moment and what is the term that would best describe what we have going on here? We haven't talked about a saturated or an aliphatic hydrocarbon yet, but we'll get to those. Hopefully if you've been doing your reading, you know what I'm talking about already. But we have talked about the term alkane, A-N-E, meaning single bonded hydrocarbon. So that is this guy. Now, the word hydrocarbon is in both of these. So we're going to go through these as well. So a hydrocarbon, like we said, there are 4 different flavors of hydrocarbons that we're going to talk about. Alkanes, A-N-E, alkenes, E-N-E, alkynes, Y-N-E, and aromatic compounds. So they all begin with A. And we break them up into these categories because they have different properties to them in terms of how they react with things, what types of chemistry they can do, what kind of properties they have in terms of boiling points, melting points, stabilities, and everything like that. The last thing I'm going to talk about in this video to end this is the concept of saturation. So a saturated hydrocarbon will be a hydrocarbon, so a carbon with hydrogens. Again, just pretend that at the end of each of these is hydrogens, where we have the maximum number of hydrogens that could possibly be represented on that compound. That means it's saturated, it's fully soaked in hydrogens. When we have a double or a triple or an aromatic compound where we've got double bonds, triple bonds, or rotating double bonds, we have fewer hydrogens than is totally possible. If I had 2 carbons, the maximum number of hydrogens I could have on it would be 6. In this case, in this alkene here, I have 2 carbons, so the maximum number of hydrogens I could have on it is 6. But I don't have 6, I have 4 because there's a double bond. So this compound is unsaturated in hydrogens. It doesn't have as many as it possibly could have. Same with this one, and same with this whole compound here. So, it's just a way to describe a compound. We'll talk about this a little more when we get to the concept of things like saturated and unsaturated fats when we talk about food. And it has to deal with this concept of double bonds or double and triple bonds or single bonds. So fats typically are long hydrocarbon chains. They might have a little bit of a doodad on the end of them, but the bulk of the fat structure, if it's an oil or an animal fat or anything like that, is typically made up of a hydrocarbon. Now, if it's an unsaturated fat, that would mean that long portion of the hydrocarbon has some double bonds in it. We don't really see triple bonds, but we do see double bonds. That would be an unsaturated fat. A saturated fat would mean that that hydrocarbon portion of the fat is no double bonds in it, and it's all single bonds. That's how we define the difference between a saturated and an unsaturated fat. We're talking about the physical structure of it and whether or not it has double or single bonds in it. All right, that's the end of our first video for chapter 11. We'll pick up with part 2 of chapter 11 in the next video.